So yesterday we talked about softwares like Seismic Unix and OpenText for seismic data processing for marine or land seismic data, and then the interpretation of those seismic data can be done using the help of OpenText software. So we talked about that, and we saw how we can download from where. Sorry for the yeah, and how we can download that software and the manuals and the data. And after that, we saw three videos, seismic data acquisition videos. So now I hope we all have a better understanding of why and how seismic data acquisition is done, and why it is important, and what are the different what do you call types of seismic data acquisition, like end-on, symmetric, split spread, and like that, depending on the depth, what kind of seismic data acquisition. So if we go for crustal studies, so we generally go for wide angle seismic data or seismic reflection data. So it covers the depth of investigation is almost 50 to 60 kilometers, and compared to that, the offset will be of around 200 kilometers to more than 200 kilometers. So if we want to image full crust up to Moho, like the first boundary between upper mantle and the crust, that is Moho. So we saw that refraction survey is used, and in refraction survey, the offset is always much larger than the depth of investigation. And we also saw that reflection survey, which is generally done for the delineation of oil and gas reservoir beneath the subsurface, and in that the geophone spacing and the depth of investigation is not that high. So depth of investigation for oil and gas exploration for marine scenario will be of 2 kilometers from the sea surface, not from the sea surface, but from the seabed. Okay, and for land, it is almost around 5 kilometers of depth, and the geophone spacing is very minimal for for delineation of oil and gas reservoir, or for reflection survey. And for refraction survey, to image the full crust up to Moho, the geophone spacing is much higher. So if we compare, now suppose I'll give you an example. Now, if I want to conduct a survey for oil exploration, so what happens is, so my geophone spacing will be of around 2 meters to 5 meters apart, interval between two geophones. But when we talk of full crustal modeling or imaging up to Moho, so the depth of investigation becomes 50-40 kilometers. And for that scenario, the geophone spacing will be of around more than 200 meters to 400 meters and 500 meters. Like it is always more than 100 to 200 meters. Okay. So now we saw the video. Now we'll be seeing the acquisition parameters for land and marines 2D and 3D surveys. So we'll be starting with the presentation now. So yeah, this is the day 3 actually. I forgot to modify this. It was supposed to happen yesterday, this presentation, but I chose, like, first I'll show you the video and then I'll continue with the presentation. Yeah, one second. Okay, so the outline of the talk will be for survey, like we'll be talking about CMP method, or it's called common midpoint or common depth point method. Okay, this is generally for reflection survey. So we'll be talking about sensors, seismic sensors, that is geophone for land, and hydrophones. These are the geophone for land. Okay, these. Okay, I have already discussed that this is a 3-component geophone, like 3C geophone. It records seismic data in vertical and horizontal fashion. So there is one vertical component and two horizontal component. Horizontal components are eastings and northing. Okay, E for easting and N for northing. Okay, and this is Z, that is depth, vertical. And this is a single component geophone, it records only the vertical component. Okay, so again, depending on what is my objective, I'll go for either three component or a single component or reflection or refraction. And mind you, like see, if we acquire a three component data set, so the parameters of data acquisition may change, and accordingly the seismic data processing for three component will be slightly different than the single component. So in this, only the vertical component is recorded for this, and we can again here depending on our objective or depth of investigation, the geophone interval will be different. Okay, for 3C and single component. And the hydrophones, this is the hydrophone. Okay, this is the hydrophone, and we'll be talking about the gimbal geophone or and hydrophones. So this is basically used. Gimbal hydrophones are basically used for marine surveys, because see, for land survey we can plant individual geophones which are connected through the wire. So there will be like yesterday we talked about 8-channel geophone, 12-channel geophone. That means the eight geophones will be connected through a wire. Okay, so 12 geophones will be connected through the wire, but there are independent geophones also. Generally, the 3-component geophones are independent, means there are no wire connected to that. There will be one GPS attached to this. Okay, to record the to locate the coordinate or the position of the geophone planted. Okay, and similarly there can be individual independent single component geophone as well. Now the question is when and why we use independent geophones. Okay, so what happens now, suppose if you go to a place and the place is like flat, so you can plant wired or connected geophones and there will be no problem. Means you can keep the geometry even. For a flat surface, you can plant geophone. Now suppose if I want to plant a geophone at every 2 meters, so and on a horizontal surface I can do that easily for wired connection. But now suppose go to a place or a hilly place or a rocky place. Now you want to conduct a survey on a mountainous region, so the land is not even or flat. So what happens is that in that case my geometry of data acquisition breaks. I cannot plant my geophones at regular intervals because of obvious reason of undulation of the topography. Correct? So far so good. So in that scenario, we use independent geophones which are not connected through the wire and they have inbuilt battery in it. Okay, so that the recording can be done. So we plant. Any questions? If no questions, Samuel, please can you mute yourself, because there are lots of background noises coming. So I was talking about now for an undulated surface, we need to have independent geophone so that the geometry of data acquisition remains even. So if I want to plant a geophone on an undulated surface at every 2 meters or 5 meters or 50 meters per se, so I can do that easily. But here, so what will happen? See, the land is uneven, so I'll have to apply a static correction and correction due to the elevation. Okay, so we'll be talking about these corrections when we'll talk about the seismic data processing. So there are two types of geophones I talked about, like wired or channel geophone and independent geophones. Okay, but in case of hydrophones, we generally use a gimbal hydrophones or connected hydrophones and geophones, like, and there are accelerometers. So basically we don't use accelerometer much. Now suppose there are a marshy area, means it's and I want to conduct a survey in that, so we can go for accelerometer, but generally we don't do that. Like we don't go for data acquisition in marshy area. And the type of sources we'll be using is explosives and vibroses for land. Okay, this is for land. Okay. And the type of data we'll be talking about is segway. There are several many format of seismic data, but the widely accepted seismic data format is segway data. So we'll be talking about that as well. No. So I talked about what kind of sensors we'll be needing for and what kind of source we will need for assessing data acquisition. Now, the acquisition parameters we'll be talking about for in the outline two of this topic of this presentation. We'll be talking about the acquisition parameter as well. So, sampling rate means at what rate the data has been acquired. Make use of the chat box. Yeah, exactly. Thanks a lot. And then offset range. So I already talked about what depending on our objectives, what could be the offset for oil and gas exploration. The offset will be of range 5 to 10 kilometers because depth of investigation is less, and that is why the geophone spacing will be less. But if I want to image full crust up to Moho and upper mantle, so we'll go for huge offset and more than 200 kilometers. Okay, so in that scenario, the geophone spacing will increase, short point spacing will increase, and for imaging a Moho, that is wide angle reflection survey or refraction survey, the offset is always much larger than the depth of investigation. Listen time and the sample. Actually, I already said the sample rate and the temporal aliasing. We'll be talking about the aliasing, geophone spacing, and spatial aliasing, and the sorry, shooting geometry. What in what pattern data can be acquired? Like if I want to go for a 3D kind of survey, so we'll be using geometry using inline and crossline. Inline and crossline are nothing but, now suppose this is my area of investigation and I want to conduct a survey in 3D fashion. So this will be my grid or lines or 2D lines. Several 2D lines will make a 3D data acquisition. So in this, now suppose I have a short point here and a short point here. So what will happen? It will be recorded by this line and this line also. So this becomes my cross line and this becomes my inline, correct? So we'll be talking about for 3D, we'll be talking about inline and cross line. And now suppose if I want to do only 2D survey, so I just have to get only one line and there will be source here, okay? And there will be geophones here, okay? Multiple geophones, okay? So that's the thing. Now we'll be talking about common midpoint method or common depth point method. Okay. So here we can see that there is a what do you call cartoon showing that the marine survey, and this is the acquisition ship. It's also called ORV, means Ocean Research Vehicle. Okay. So, and this is the air gun or water gun, and these are the geophones. Okay. So what will happen? The air gun will blast the energy and it will be recorded by these. Okay. And why it's called midpoint? What happens is, like the data now, for first geophone and this water bubble, this will be the midpoint. So the midpoint of these first geophone and the water gun or air gun is illuminated by the wave and it is recorded. So So it will always be the midpoint of the uh, air gun and the corresponding geophone or hydrophones. Okay, so that is why it's called common midpoint. Okay. For this also, for all the geophones and all the corresponding geophones with air gun, the data acquired will be acquired by eliminating the midpoint of the corresponding geophones and the air gun. As you can see here, as I already showed in the previous slide. So this is the first shot, this is the second shot, this is the third shot, and these are always at the midpoint of the air gun and the hydrophones. See, you can see here the separation between the geophone and hydrophone is always half of the distance between the air gun and the hydrophone. And now this becomes my offset, means the from shot point to the last hydrophone or geophone becomes my offset. The classification of first two geophones shown in the outline. Oh, okay. So this is a 3-component geophone. Okay, and this is the single component geophone. Okay, so you can message for everyone, not the direct message, so that everyone can see the kind of questions you are putting, and accordingly everyone will be benefited. See, you can see here there are 3 spikes: the first spike, the second spike, and the third spike. Okay, now if you guys have studied about seismology or seismometer, if you know the working of seismometer, so what happens in seismometer or seismogram? So what happens are there are 3 sensors perpendicular to each other, means there will be an orthogonal, like I'll switch on my video so that you can see the example. Okay. So for seismograms, what happens is, now you can see that so this is the vertical and this is the horizontal. This is the vertical and this is the 2 horizontal sensors. Okay, this is the working of seismogram. Okay, so what happens, that is for recording earthquake waves for vertical northing and eastings. So we took the same concept to make a 3-component geophone. So it acquires data in 3 3 perpendicular directions or orthogonal direction. So this is vertical. Okay, and this will be the northing. Okay, so this will always be pointed towards the north of geographical north, and this will be always pointed towards the geographical east. Okay, so what happens is that the data will be recorded vertically, and then in the northings and then the eastings. Okay, so there are 3 sensors orthogonal to each other, and all these sensors will record the particle motion in vertical direction and eastern northern direction and eastern directions. Okay, now suppose if my so this is my north. Now suppose this is my north. Okay, north, south, east, west. So and so what happens now, suppose if my profile is along this, so what will happen, suppose if my profile is this, so and I acquired a data, so what will happen, we'll have to rotate this. See, for processing the data or modeling the data, so data is acquired with the help of geological coordinate or geographical coordinate, but when we process the data, we process according to the azimuth of our this profile. Now suppose this profile makes a 90-degree with the northing, so what will happen, the angle between our profile and the northing is 90 degrees. So what will happen, will rotate the traces from northing to according to our azimuth of the profile. So the northing will take the northing and will try to align it with our profile. So northing will move it to the clockwise direction. So northing will become radial because it will be following our data acquisition profile, and the easting will become transverse. So now suppose if this is my easting, this was my easting, so the easting will be rotated to become transverse component. So it will be again rotated by 90 degree, and so this becomes my transverse component. Okay, so these 2 are northing and easting, or radial or transverse, are my horizontal components of the data. Okay, and the vertical remains the same. Vertical will always be vertical. Okay, because we are rotating on the ground, not in a 3D fashion. Okay, so this is the concept of three component geophone. And why I am talking about the radial and transverse component, because the data will always be acquired with the geographical coordinates and geographical coordinate system. But when we process the data, we'll have to consider the azimuth of our profile. So azimuth is the angle between the north and our profile. So our profile can be straight or our profile can be like this. So the azimuth will become this. So it can be anything. Okay. And for vertical component, we don't have to go into this these complications. So we will have only, we can only get the vertical components, only the vertical component, and no, this will be only the vertical component and no horizontal components. So I hope I answered your questions. If this is clear, could you just say yes, Kachi, or type yes, so that we can move? Yeah, great. So I already talked about this short point location and the hydrophones and the midpoint. What is the common midpoint method? This is also called common depth point, CDP. Why it is called common CDP? We have talked yesterday, because the data is acquired on a what do you call same datum or the same layer. Okay, flat horizontal layer. So that is why it's called CDP, common depth point. Okay, so depth for each short point will be same. Now suppose if the depth is around 5 meters, so the depth of illumination for all the shots or the rays will be 5 meters. Okay, so that is CDP. So and see, I'll come 4 or 5 slides. I will play. I'll move fast so that you can see. This is the short point 1, and this is the short point 2, short point 3, short point 4, short point 5, short point 6, short point 7. Okay, 8. So what you saw, that the ship is moving. The ship is moving, and so is the short point. See, this was the initial position of my short point 1. So this becomes SP1. Okay, short point 1. Okay, then short point 2. This becomes my short point 2. Short point 3, short point 4, short point 5, short point 6, short point 7, short point 8. So you see that how marine seismic data is acquired. Now the thing is, now suppose marine seismic data is always is acquired in a 3D fashion. So what will happen now? Now suppose this is a ocean. Okay, this is a part of ocean, and my area of investigation is this within the EEZ. Okay, I want to acquire the data in this area, particularly only in this area. Okay, so what will happen? So what will happen is, now suppose the ship is initially, the ship is here. Okay, so what will happen? The ship will move like this, and then again it will move like this on the same profile as planned, and then this, and then this. Okay, so it continues. So what is happening? The data is acquired continuously along this path. Okay, this is for the inland, and then again it can be like the ship can move like this, and finally end up here. Okay, so meaning to say is that the data is continuous, and the short point is recording is also continuous. Okay, and the combination of these hydrophones is called streamers. So the hydrophones are connected with the streamer. So there can be lots of multiple streamers for a 3D survey. Now suppose if I have only 1 or 2 streamers, so I'll go in this fashion. Okay, like this. But if I have multiple streamers attached to a ship, so at one go we can acquire multiple data set, not only of line but of multiple lines. So the ship will not have to the spacing between the 2 lines will not be, now suppose if only 1 streamer is there, so spacing will always be less because I want to what do you call, acquire the data on a very less spacing, so that the similar yesterday we talked about fold and area of illumination and stack section, sorry, stack of the data acquisition. So in that, what we studied was like one particular point is illuminated multiple times, so it will give, for one particular point will have lots of data. So for that we need the spacing between the data acquisition lines will be should be less. But if I have multiple streamers attached to the board, so what will happen? It will decrease the cost of data acquisition, because in that scenario, I can, this ship can like move like this. It can cover huge area at only in a single time. So keeping the cost also in mind, so we have to plan the seismic survey. Okay. So for short point one, we saw that for in these for short point one, this was the position of short point and hydrophones. So we'll be talking about short point locations and midpoints of short point and the hydrophones. So for short point one, then for short point two, it moved ahead. Short point two, short point one was here, and then the ship moved ahead. Then the short point two is here, and likewise the hydrophones also moved. Okay, then short point three, short point four, short point five, and so as you see, as the short point moved, what I have, the geophones, hydrophones also move. So area of illumination for each midpoint is like, for this there is only one ray was sampled here. For this, two rays were sampled. This was three rays sampled, and for this rays were sorry, six rays were sampled for these particular midpoints. Okay, so I have huge number of data sets for this particular midpoints. Okay. Okay, so we have already seen yesterday how it is, what are the how we can use the stack, data acquisition stack. We have talked yesterday itself. So if you have any question, you can ask, or I'll move ahead. Okay, so this is the stack, sorry, fold. See, this is the data acquisition stack, and this also gives the fold. So we see here the maximum number of data acquired in this particular zone. Okay, so number of rays sampled is 4 here, and here also it's 4, and then sorry, and it's decreasing this way and decreasing this way. So my fold is like, see, you can see here the maximum number of data set for this, and it's shown here. For maximum it's 6, 6, 6. For these three it's 6. So these midpoints have maximum number of rays, and then it has started tapering. Okay, this was for common midpoint survey. So what we know, like fold is the number of times the same midpoint is sampled. Okay, so we have talked about this yesterday, and after that there will be a decrease in the sampling of midpoints as we move from starting position to the end position. Okay, so talked about all these. Now yesterday we also saw that there was a data acquisition of end on data acquisition, or asymmetric data acquisition. So in that scenario, the fold range was more compared to the common midpoint or the symmetric data acquisition. Correct? Okay. So the maximum fold here achieved is 6, because means these midpoints have been sampled 6 times. Okay, and as we move to either side, the data sampling of the common CDP or CMP or common midpoint is decreasing or tapering down. So the maximum fold is recording group. Yesterday we have seen this, and the distance between the groups and the distance between the shots divided by 2. This will give you the maximum fold. This is the simplest formula. Yesterday we talked about it, took many things in consideration, but if you want to understand this with this formula, you can understand the fold of first seismic data acquisition. Okay. Now moving on to the next slide. Okay. Types of gathers. So yesterday, if you remember, I said that there different types of gather. That is, one is short point gather. Like for each short point, I will connect the traces to make the short point gather. Like for short point one, there now suppose if we go here, yeah, there's for short point one we have six traces. So I'll combine these six traces to make one short point. Now, if I want to combine, so what will happen? This is my suppose this and this and this. Like, I'm sorry for the I'm what do you call, drawing on a trackpad, so it's looking bad. So this is my short point one. Okay. So it will be having six traces. Okay. So again, and then we'll have common source receiver gather, offset gather. So common offset source receiver. So what we understand, common source and receiver offset. Okay. So the receiver and the geophone offsets are like for a how should I put it? Source receiver offset. I will have to go back. Yeah. See, in this section, this was the initial position of my short point one, and the short point two moved here, but the first hydrophone comes here. Okay. So considering this geometry, we make the offset receiver gather, but this is not so common for seismic data processing. We only go for short point gathers and the common midpoint gathers, which we have already seen. Short point gather and common midpoint gather, depending on our types of data acquisition. Like suppose if I'm acquiring symmetric data set, like and split spread, like equal number of geophones on either side of the short points. Okay, so we can have common midpoint gather for that. Now, if I want to go for end-on or asymmetric seismic data acquisition, so we can have short point gather. So depending on our type of survey, we can make this short point gather and common midpoint. And there is one more what you call term, that is FFID, that is first field identification. Okay, so either we can use short point gather or source receiver gather or common midpoint gather or FFIDs to process the data. And why I'm talking about this now, suppose when we process the data, we need to have the geographical coordinate of the data where the data was acquired. So we'll feed the coordinate system into our system for while processing the data. So it will give me the exact location where the data has been acquired and what was the position of our geophones, so that it will be helpful for us when we do the geometry merging or the elevation correction. Okay, so for those reasons, this short point gather information or common midpoint or FFIDs are important. So this shows that what is a short gather example of a short gather. Okay. This is a short point gather example. Short point 3. Now we saw that for the flat horizontal layer. But now suppose if I have a dipping layer, for that scenario, what happens is the midpoint changes. Now, see this. See, this is the midpoint. This particular point is midpoint for these combination of hydrophone and short point. But the data was up. The ray hits here. Okay, correct. So in that scenario. So in that scenario, what we do is like we go for common source, like the second one, this common source receiver offset gather. Okay, so for that scenario, we go for this. But generally, we don't do that because what we'll do is we apply migration to the for a dipping layer, and we try to again we go for the CDP or CMP. Okay, for all the shortcuts we'll be seeing in the next coming slides. Yeah, if you have any question, please. So for a flat layer, we have CDP or short point gather, but for a dipping layer, we have common source receiver gather, offset gather. Okay, for a dipping layer. COS can also be for flat layer. So, but that's a general question. Sorry, general what do you call situation. I'll have to have some water, please. Please bear with me. I'll have water and then I'll come back. I guess charger देता हूँ. ये लीजिए. Where is the video section? Okay, sorry for that. Okay. So far so good. Any questions? No questions, so I'll move. See again, I talked about will apply the migration for a dipping layer. Okay, so what happens? The actual midpoint for any short point is this, but the rays are eliminated here or hits the surface here. So for that scenario, what we have to do is there is a change in the we'll have a perception or the data give us the perception that the depth of investigation is different than the actual depth. So in that scenario, we'll have to apply migrations. Okay, depth migration. So what happens in the depth migration? Generally, what happens in the depth migration? We try to bring the actual what do you call the point of illumination to its actual, like now suppose the ray strike here, but the data shows us the depth of the reflector is here. So what we try to do is we try to bring this pseudo or the acquired reflector from here to this actual position by applying depth migration, which we will see in the coming scenario. Now this is the common midpoint. It's a very generalized what you call depiction of the midpoint. Now see, for each geophone, okay, geophone and short point and hydrophone or geophone, this is the midpoint. Okay, MP. We'll write this as MP. Okay, so what happened? The survey is not generally done in this fashion. For why? Because now for each short point, I'll have to have only one geophone. But this will be very costly. So what happens is it's a very generalized form of depiction of midpoint, common midpoint survey. So what happens? The geophones will always remain same. Okay, and as the short point moves, geophone is also moving. So for that scenario, there will be like a common midpoint for each corresponding to each short point and each geophone. Okay, so if this is clear, I'll move to the next slide. Let me show you with one example. So initially I showed this was the initial position of short point one, then and this was the midpoint for this, and this was the midpoint for these. Okay, so as this move, what happens? The midpoint for this changes, and midpoint for this midpoint between short point 2 and the geophone 2. is equivalent to the midpoint of short point 1 and geophone 1, which is here, correct? You see my one second. See, this is the position of my pointer. So as we move, my pointer remains the same. That means for a different scenario like short point 1 and for geophone 1, this was the midpoint. But as the shape moved, this was the short position of short point 2, and this is the midpoint for the geophone 2 and short point 2. So if this is clear, we'll move. See how the midpoint is varying for each corresponding geophones and short point. See my this pointer is staying at the same position, but short point and geophones are changing. Yeah. So moving on to the next. This was done. This is done. This is done. This is done. And for dipping layer also we can have a common midpoint. Okay. Similarly, as we talked, so in this scenario, what happens? So in this scenario, since we are illuminating only one position with different short points and geophone combination, we can have a common midpoint for a dipping layer also. And what and how it is useful, like common midpoint for a dipping layer. So what happens for one particular position? There are n number of data points. Okay, so that means like this point has been sampled 8 times. So when we will apply migration and the stack section, so what will happen? It will give me the actual position of the reflector. Okay. See, this is the true reflector position. Okay, means the midpoint for a combination of different geophones and short points. So the data is acquired like here and here. So as we move, the midpoint changes. This is the true reflector. This is called true reflector. But if we take the midpoints, so that means that for each short point and geophone, this is only the midpoint. Okay, so we'll be seeing all these how we can apply migration and NMO to get the midpoint or to bring the actual position of the reflector to its actual position rather than the acquired position, data acquired position. And see, I already said that. Now suppose what happens if this particular position has n number has been sampled 8 times, so I'll have 8 traces or 8 data corresponding to this particular position. So when we stack all the data together, so what will happen? So the signal to noise ratio will enhance. Means that, now suppose yesterday I talked about with an example, like if a class has 2 students and a class has 100 students, and if we try to take an average of their performance, so the like a class with 100 students will give us more accurate depiction of the performance of all the students. Okay, so that means if we stack the combine all the data for one single point, what will happen? The what is the signal to noise ratio will increase multifold. That means that particular point will be resolved with high resolution. Okay, and it will get a fine structure or fine image of that particular point. Okay, that is why CDP or CMP method is very much important in oil and gas industry. So we have talked about types of method, and we'll be continuing with the CMP method. We have already talked. Seismic sensors we have talked. Geophones, hydrophones, gimbal. We have talked about all these. We'll be talking about explosive, but first, before going to explosive, we will be talking about the gimbal hydrophones actually, or geophones, or working of the geophone. Yesterday, I asked you to look for the what do you call working mechanics of a geophone and a hydrophone. So, and I explained also, I gave a hint also. So what happens? This is the internal part of the geophone. So geophone on the from outside, it is surrounded, it is covered with a plastic what do you call material, and with a spike. That spike goes into the ground. Okay, but inside that we see this kind of structure attached to that, attached at the top of the now suppose this is my top layer of the geophone, or the plastic layer of the geophone. So this particular thing will be attached to the top of that or the bottom of that geophone. So what happens, it has a magnetic a magnet, and that magnet is surrounded by a coil. Okay, so what happens whenever we like what see, do we are we familiar with the concept of electromagnetic flux? What happens whenever there is a change in magnetic flux around a coil? So electricity is generated, electric current is generated, correct? Okay, so that current is converted into like ground motion. So whenever there is a ground motion, or when we what you call use explosive to generate seismic wave travel through the uh, 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 different layers of the surface, and it is received by the geophone. So basically what geophone measures is like the motion of the ground. Okay, motion of the ground. So if you now suppose if you are what do you call it, sitting on a chair and a table, so keep one hand on the table, and from other hand just tap on the table, so we will feel vibrations. Okay, so the same thing happens when we when the geophone receives the seismic wave. Okay, so that means the ground motion when we explode or when we blast the explosive or air gun, so seismic waves are generated with huge energy, and that particular seismic wave causes the ground to move. Okay, or the particles of the what do you call subsurface moves in different directions. Okay, for P wave and S wave, so that causes the ground to move. So, and because of that, what happens is like the coil or the electric coil or the magnet. See in this particular thing, so either the magnet will be fixed and the coil will be suspended with the help of a spring, or coil will be fixed and the magnet will be suspended with the help of a spring. So whenever there is a ground motion, so what happens, either the magnet will move along the fixed coil, the magnet will move along the fixed coil, or the magnet will remain constant and the coil will move. Okay, so what happens in both the scenario, there will be change in magnetic flux around the coil. Okay, and because of that, electric current will be generated, and that will be converted to the ground motion. Okay, and that was the working mechanics of the geophone. But when we talk of hydrophones, can anyone tell me what was the concept behind a hydrophone or working mechanics of a hydrophone? I talked about yesterday. So if you guys were present yesterday, so please type and into the chat box. Otherwise, I'll not move to the next slide. Here, a hint is given here. So please type what was the working mechanics of a hydrophone, and then we will move to the next slide. Come on. Anyone? Unmute yourself and you can tell me. Okay. No issues. I'll take. So, see, what do you call magnetic flux or magnetic flux concept cannot be incorporated for a hydrophone, because the streamers of the hydrophone always be on the surface of the water and it will always move. Okay, so what happens, it will record unnecessary readings. Okay, so that will become noise. So what we use piezoelectric effect. So if we remember from our graduation or bachelor's degree, what is a piezoelectric effect is like if there is a change in pressure along a coil, so what happens is that it will create electricity in that particular coil. So a hydrophone works on the principle of piezoelectric effect. So when an air gun is blasted, huge amount of pressure is released, air pressure or air bubble is released. It goes down and hits the ground and then gets reflected back. So and it comes with the with a vigor. So what will happen? The hydrophone receives that air gun pressure, and there is a change in pressure inside the hydrophone. So that causes the electric currents to produce through the coil, and that will be recorded as the motion or the as a seismic wave. So this is a gimbal geophone hydrophone, means it has geophone and hydrophone inbuilt in this, but this is only used for a bottom simulating reflector server, like BSR kind of server. So these are planted on the ground, means on the not on the ground, on the sea bed. Okay. So and these are connected with a continuous recording system, and these are left lying on the seabed for 2, 3 months, 4 months. Okay, so that it can, and the ship will move on the top of it, and then it will blast, and the pressure will go down, and it will record the change in pressure, and also the ground motion will also be recorded with the help of geophone and hydrophone. So this is very much important, means this system, gimbal system of geophones and hydrophone arrays are very helpful for delineating of any presence of gas hydrates. Okay. Gas hydrates and oil and gas reservoirs. Okay. 1 second. Yeah. So moving on to the next slide. Again, this is an example of 60 hydrophone. See, this hydrophone also works by converting the sound wave into electrical voltage by detecting changing motion. Yeah, exactly. That's called piezoelectric effect. Okay, so it works on the principle of change in pressure of the surrounding, and that because of that, electric currents are converted. Very good. Yeah. Again, here is an cartoon showing the data acquisition of this like of a streamer. So this is a streamer having like 60 hydrophones, or like a number of hydrophones, and then there will be a blast, and this will be recorded here. And see, these are the gimbal geophones, like these are lying on the ground. Okay, and so these are two scenarios it's showing here, and this is called the streamer, and this is the gimbal. Sorry, my mistake. This is not the gimbaled one. See, this is the streamer, and it's very huge in length. So they are just showing the number of means in a very expanded form. Like this is the magnified form, and it's after here it's not showing anything, but this is showing the complete image of the what do you call streamer. Okay, and one more thing is like, see, you guys have a very good opportunity regarding, see, Indian government organizes like expedition to Antarctica for 6 months, and also many expeditions for 2 months, 3 months in Indian EZ, and it's open for all the international students and national students as well. So you can visit this site of NCPO. NCPO, yeah. This stands for National Center for Polar and Oceanic and Antarctic Research. So I got an opportunity to go on an expedition in Arabian Sea for 2 months by this organization. So it's and this organization is an Indian organization, comes under the Ministry of Earth Sciences. So it conducts multiple expeditions around the world. So you can just go to the site of this NCPOR, and you can see whether you can apply or not, and what are the different expeditions coming out. You can also go for a 6 months Antarctica expedition that can be your that can boost your CV. Okay, so you can check this site or website of this particular organization, and you can apply for that. So it will be a good learning experience, and they do all kind of survey, like from seismic to gravity, magnetic, and what do you call sound profiling, core sampling, and everything. So it will be a very good opportunity for you guys, and you guys should not miss it. So moving into the next slide. So we completed all these. Okay, we completed all this. Now we'll go on to the sources. What kind of sources we use? So we use see, we have already talked in the first class itself. There are different sources of use for active seismic survey. Like one is vibrosis, then thumper, and then explosives for land survey, and then water and air gun for marine survey. So this is the frequency, like this is the kind of what do you call vibrosis is a how should I put it? Okay. So there is there will be a machine, and it will hit the ground multiple times, like very fast and with lots of pressure. Okay. So what happens is, like when you do like this, so it will hit the ground, and it we can control the frequency of vibrosis. So depending on our survey, for generally this is used for near surface, like only 1 to 2 kilometers or 3 kilometers. We use vibrosis, and we can control the speed and the frequency of this vibrosis, and so that we can go to a certain depth depending on our objective. Okay. And but the thing is with the vibrosis is that depth of penetration is less, and like transducer. Yeah, kind of. Yeah. This is for transducer is for like for hydrophones. He meant to say. Okay. So this was the concept of vibrosis. The depth of investigation is not that much high, and the resolution of the surface will also not be that good. Okay. See, this is the vibration of the caused by the vibrosis, and this is the kind of data acquired. So this is an example of a vibrosis or a vibrated truck. It's called vibrosis. And see this mechanism, this particular thing you see here, it's a square shaped what do you call it, flat surface, and this is the whole mechanism which vibrates this particular plate, okay, onto the ground, and the data is acquired. Okay, but the only thing about this system is that, now suppose if I'm hitting the ground with at higher frequency or with multiple times very fast, so what happens? There will be some movement of this truck also, so that can cause what do you call noise into the signal. This is an example of explosive. This is called charge. Okay, so what happens is, we dig a hole for a wide angle seismic survey, or for a, like if I want to image full crust. So what we do is, we gather or we connect multiple charges. Okay, these are explosive charges. So we connect multiple charges of size like 100 kgs, even 200 kgs or 1000 kgs, depending on the depth of penetration, and then we dig a hole of in a circular fashion. So now suppose there will be one hole, and then there will be multiple holes around these holes. Okay, and we'll plant these explosive in these holes, and then we cover these holes with sand and water, so that when we blast the explosive, the surrounding surface or the damage to the surrounding will be of minimal will be minimized. Okay, so this is a example of explosive. See, this is a reflection method, or you can say refraction method also. This is an actual seismic acquisition system cartoon. So here it's showing that they are acquiring the data with the help of vibrosis. Okay, so vibrosis, the data is acquired on by thumping the ground. Okay, but for case of like using of explosive, we dig a hole up to 20 to 30 meters below the ground. Okay, and then we plant the explosive here, and then we cover it with sand and water up to the full. Okay, and then we blast. So what happens? The waves travel directly to the geophone, and then it goes and gets this is called refracted. Okay, and then there will be reflections also. Okay, there will be multiple reflections, refractions. Okay, and there will be direct arrival also. Okay, sorry. This is not important. So we talked about the vibrosis and explosive. We talked. So now we'll be talking about SegWide data. So I'll explain what is a SegWide data. So now suppose you went to a survey, seismic survey. There is a geophone here. Okay, and the seismic trace looks like this. Okay, so this will be my first reflector, first surface. This will be my second surface. This will be my third surface. I'm just for the sake of understanding, I'm saying all this. Okay, but this is in the form of trace. Okay, so but the data is acquired in a digital fashion. Okay, so digital fashion, it has numbers. So the SegWide data, so this looks on the system. So if I want to see a SegWide data in my assessment data processing, it will look like this. Okay, like a seismic trace. But when the data is acquired, it acquired in terms of numbers, like lots of numbers. Okay, so the numbers has a header file. Header file will give all the information regarding the geometry, location, and everything of that particular geophone. Okay, and okay, and then there will be recorded travel times for corresponding to each what you call reflector. Okay, so the seismic data is like there will be a header for each trace. It will have information regarding the position, location, and geometric parameters and everything. So this is how a geometric data, SegWide data looks like on the paper, not on the system. In system, it looks like a seismic trace or like a wiggle trace. Oh God, it's a lot. So time sample rate now. So while data acquisition will have to be very conscious about data acquisition parameters now. So we should be very particular about the sampling interval. Okay. So now suppose sampling interval is the with the data acquired in a unit time, or the rate of acquiring of the data per unit time is called sampling interval. Okay. So sorry, sampling rate. So our sampling rate should be optimum corresponding to the with respect to the objective, our objective or depth of penetration and everything. We have to keep the sampling interval or sampling rate. We'll have to plan what kind of sampling rate will be like. Now suppose if I it could be like 2 milliseconds or 4 milliseconds. Okay, and why it is important to take care of the sampling rate? Because now there is a concept of aliasing. So and the Nyquist frequency. So what happens is like if my sampling rate is higher or lower, so it will create some kind of noise or the repetition of the higher frequency or the lower frequency after a particular frequency. Okay, so now suppose if my total frequency range is 100 hertz. Okay, so the midpoint of the 100 hertz is 50 hertz. So that particular frequency of 50 hertz becomes my Nyquist frequency, means maximum allowed frequency. And after 50 hertz, all other frequency is just the repetition of the lower frequencies, lower than 50 hertz. Okay, so we'll have to remove this higher frequency using filtering and everything. So that is why to avoid any, see, Nyquist frequency and aliasing will always be there in that data. Okay, but we have to minimize it. Okay, so that is why sampling rate and the sampling interval is important. Offset range, see, this is the sampling. Now either you can take from here to here, that could be a sampling interval. Like, meaning to say is that now suppose if this is my amplitude and this is time. Okay, so if I want to acquire data here, every point, like here, so what will happen? My sampling rate is increasing. Okay, that will cause a problem because the huge amount of data will be there, and it will be difficult to store all the data set. And if I want to acquire data, sample the data here on here or here, means at sparse position. So what will happen? The resolution of the data will decrease. Okay, so we'll have to be very conscious when we will decide the sampling rate of the data acquisition. This is just what I just discussed. See, the increase in the sampling rate. So what happens is, like, if I have a huge sampling rate, so there will be huge amount of data set, and it will be very difficult to acquire it, and the aliasing will be also higher. And if it is less, then the resolution will be very bad of the data. So we'll have to be very conscious. So generally what we do is we keep almost at least the twice of the wavelength as a sampling interval. Don't do that. So I talked about the Nyquist frequency. Nyquist frequency is the maximum frequency allowed in the data acquisition. After that, what happens is aliasing takes place. Now suppose this is my frequency range. Okay, so what happens? And this is my Nyquist frequency. Okay, I'm just showing with an example. So what will happen after Nyquist frequency? This data point will be similar to this data point. This data point will be similar to this data point. Okay, so we have to, and that acts as a noise. So we have to avoid aliasing. That is why the concept of Nyquist frequency is important. So Nyquist frequency is always half of the sampling rate. Now suppose if my sampling rate is 50 milliseconds, 2 milliseconds. Okay, 2 milliseconds. So that can be converted into what you call frequency. Frequency is what? Frequency is inverse of the time. So, and see, Nyquist frequency is in terms scale of frequency, but sampling rate is in terms of time. So what we have to do is we have to convert the sampling rate from time domain to frequency domain. Okay, and then we can find the Nyquist frequency. Now suppose if I have a 2 milliseconds sampling rate, that can be converted into frequency by like t, frequency is equal to 1 by t, that sampling rate, and then we'll have the frequency range of the data, and then we can find the Nyquist frequency by dividing that range by half, or dividing by 2. So that means Nyquist frequency is the half of the total frequency range. Okay. Offset range, I have already said, depending on our target, the range of the offset and the size of the charge increases. Now suppose if my offset is less, so I'll use less charge, means like 50 kgs of explosive or vibrosis, frequency will be very less. But if my offset is very huge and my depth of investigation is very also huge, so I'll go for multiple explosive combined together, and will blast it all together, means all around, means at one time. Okay, so I'll combine all the explosive and will make a huge charge of 100,000 1,000 kgs, and then we'll blast it, and then we can get it recorded. Again, this is nothing but what I have already discussed. Listen time is twice the target time of the safe. Now suppose what happens is, like I have already discussed that the geophone, the recording of the travel time at the geophone is a two-way travel time. Okay, so it means the wave goes down and then comes up. That is listen time. It's not that. Especially aliasing. Sorry, I'm getting thirsty. Okay. See, we talked of the Nyquist frequency. That was regarding the sampling interval. So, the similar concept is applied for special aliasing. It's like in space domain. So, what happens is like here we don't talk of the frequency, but we talk here of the special frequency, not the sampling frequency. Okay. So, if special frequency or the wave number, okay, is the cycles per second unit distance. Like now, in 1 unit, how many waves passes through that particular particular distance. Okay, so that gives the wave number, and the what you call sampling aliasing or Nyquist aliasing wave number can be computed by the half of the CMP spacing, like total CMP spacing, common midpoint spacing. Oh, thanks a lot. So if you guys have any problem, you can just let me know that I can re-explain the things. Okay. So just like Nyquist frequency, this is the what do you call spatial aliasing or Nyquist wave number. So it is the half of the CMP spacing, which we have already seen. And what is the CMP interval? CMP interval is nothing. Now suppose if this is one, okay, so this is one first wave, and then there is second wave here, also second amplitude here. So the wavelength from here to here, for computing CMP interval, we have to take the wavelength. Lambda is nothing but the wavelength and divided by 4 sine theta. So that will give me CMP interval. Okay, and this is used to compute spatial aliasing. Now suppose as I already said, so this is my sorry, yeah, this is my wavelength. Okay, and this is the angle of receiving the, like, see what happens. The wave is propagated and received at the geophone and by the short one and the geophone as particular angle. So that angle, if we know that angle or for any angle, we can compute like, see, if this is theta, so we can compute x and this portion also. Okay, so CMP interval will give me the wavelength, that is v into t. This is v into t, that is velocity into time. Okay, divided by this particular thing. So this will give me sine theta. Okay, sine, if we apply the formula, so we can compute the sine theta. So from this this offset or the interval between the two CMP or two geophones or hydrophones. Okay, okay, and divided by the wavelength, velocity into time, we can take, will give me the sine theta. Okay, and then from sine theta we can compute the we can compute the aliasing or special aliasing, and this is just what I have already discussed. Sorry, my energy is getting low, but we are nearing the end of this session. So what is why special aliasing is important? Special aliasing is important just to, for the, now suppose if my special aliasing is like, if the data gap or the interval between the two geophones is huge, so what will happen? It will degrade the stacked sections, like this the resolution of that particular area will decrease because the data is sampled at a very huge space. So if I have spacing, I mean, geophone interval or the spacing between two geophone is close enough, so we'll have a higher resolution. So that is why spatial aliasing is important, because it will help in means what you call concept of, or taking care of spatial aliasing is very important, as it will help us in getting high or good resolution seismic data. And signal to noise ratio is computed with the help of like CMP fold into the vertical stack. I have already said that what happens is, like, if I have multiple seismic traces, they are combined for one CDP or CMP. Okay, for one point, if I have multiple, if that midpoint has been sampled multiple times with multiple waves, so those, but all those waves for considering pertaining to one CDP or one particular point is stacked together. So what happens when they are merged together or stacked together? So what will happen? So that particular point, the data point for data for that particular point will increase, and that will increase my signal to noise ratio. Means that means signal will increase and it will suppress the noise. So shooting geometry I have already discussed with the help of this. So I will not discuss about the shooting geometry here again. See, shooting geometry I have already discussed. Yeah, here also. And this was for sea, and for land also we have already discussed. So we'll not go into that shooting geometry. And you just have to take care of two things, like spacing of the geophones, undulations of the topography where you are conducting the survey, and location of that particular place. Okay, and then you can for 2D survey there is only one line, and for a 3D survey we'll have inline and cross line. They are mutually perpendicular to each other. Okay. So all these all are for 3D, and it's equal to like which we have discussed for 2D, but it will have 3 coordinates, whereas 2D had only x, y, and here it will have x, y, z for 3D fashion, like x, y, and vertically down. And sorry, for 2D it will have x and the z. Okay, but for 3D it will have x, y, and z. Okay, vertically downward. Okay. So you can compute the CMP for 3D survey also, source receiver offset also for this. For azimuth also you can compute. Digital signal processing we'll be talking in the next class. So for this, if you have any up to this, if you have any doubt, please let me know. You can ask questions. I'll be happy to answer any questions. Thanks a lot for bearing up with me, and I'm sorry for the inconvenience. I had to go for water. Okay. So if you have any questions, you can ask. Kindly unmute yourself, and we can have a discussion. You guys have energy left in you, then we can have a discussion. Yeah. Guys, the class was so boring that you guys all slept.
We have not slept.
I made you guys sleep.
We have not.
Yeah, I'll stop sharing my screen, or if you guys, does dipping angle of the subsurface structures ever has an impact on the seismic survey wave? No, it doesn't. See, the only problem with the dipping surface is that when we acquired the data and when we take it for processing, so what happens? It gives us a false notion of the actual dipping layer. I'll give you an example. Now, suppose this is my actual dipping layer. So that when the data is acquired, it will give us a perception that the reflector is here, not here, but the reflector is somewhere here. I will show you if I have kept that slide here for one second. Yeah, I'll show this. See, this is a shot gathered looks like. What happened? I'll show that example. Now, see, I'll show you an example of a dead dress. So this is an example of a dead dress. Can you see the slide? Okay, but no, that is not the question. I'll show you if I have here in this book. So, I'll show you with one example I have. I guess I had this. I'll show you with an example. Yeah. See, this particular thing. So this particular thing. So we see here there is an syncline and there is an anticline. Okay. So and this is the data acquired for syncline and anticline. So it gives us what do you call false notion of the depth of the reflector. So that is why we do seismic migration for a dipping layer, which also can be seen here. Yeah, yeah.
So I can't see your screen, sir.
Hello?
Can't see your screen, sir.
You can Oh, sorry. Wait. Oh, I have stopped sharing. Sorry. My bad. See. This. Yeah. See. This is the actual reflector. Okay, and this is the data. These points were sampled. So when we take the seismic data, it will give us the false location of the actual reflected. So what we do is we try to bring that what do you call for a reflector from the data from the recording point to its actual position. So the problem with dipping layer is only this, that we need to apply migration, because in case of dipping layer, we get a false notion of the position of the dipping reflector. No. Elevation correction is different. So elevation correction is for the topography, top of the surface. Okay, not with the subsurface. Okay. So elevation correction is done for the topography or the top surface, on the subsurface where the geophones are planted. But for migration is considered for the subsurface. So I hope I answered what you wanted to ask. Any more questions? Any more questions? So shall we end our discussion today for today? And one request, please download that Seismic Unix and open it and start practicing on it. We'll be talking about signal processing in next class. So with this, I'll end my session if you guys don't have any more questions. So it was nice talking to you guys, and thanks a lot. Thanks for bearing with me. I hope the class was interesting today. And sorry, I I stretched it for almost 1 hour and 45 minutes. But if I'll not explain things in a better way, it will be of no use.
Thank you very much, Deepak. Can you hear me?
Thank you very much, Deepak.
Hello, can you hear me?
Yeah, we can hear you. We can hear you. Yeah, we can hear you.
All right. Thank you so much. We are very grateful, Deepak. Thank you so much for your efforts. Um, I am sure that all the participants has learned a great deal in Seismic, and I'm sure that they will put these things that you are teaching us into good use. I also want to remind everyone that the SCG informative session is going to be on Friday by 3 p.m. West African time. So don't miss it. Tell your friends, tell your school to attend, so you can meet the SCG president and ask her any questions that you want to ask her. Okay. I think that's the end of our meeting today. So we are going to meet next week the same
Oh,
time.
what is like softwares you are asking? The software link I already shared with you guys. You just or I'll send a link to Radiat and she can circulate it to you guys. Okay, and you can download it from that particular link. And all these like videos or what do you call presentation is always it's already recorded, so it will be shared to you guys by the coordinators. So, and one more thing, please visit that website I told you about, NCPOAR. You can get a chance for an actual expedition and you can learn data acquisition and processing for almost all the geophysical and geological surveys like gravity coring, VSPs, uh, gravity, seismic, bathymetry, seismic, everything. So please visit this website of this particular organization. It's an Indian organization, and it's open to all the students across the globe and scientists. So this is the organization name. I'll show you also on website, and it is located in Goa. So Goa is the holiday destination for all the people from the globe. So see, from here you can see expeditions. You can go to NCPO's website and on the under expeditions you can check which expeditions are going to happen in the coming past. And yeah, NCPOR, sorry, NCPO, not AR, NCPOR. Oh, yeah. Yeah, Polar and Ocean Research. Yeah. So please visit the site, and it's open to all the people from the globe, and it will be a very great thing for you guys, and it will make the CV very strong. Okay. Yeah. What do you guys? I'll stop sharing my screen.
Thank you very much, Deepak. Thank you very much. I'm going to share the link to the others, and we'll get back to you if you have any questions.
Yeah,
So
sure.
I'm passing the mic to you now, Uzoma. Uzoma. Or is there any other president on the call that wants to say something? All right, in the absence of no,
Okay.
your mic is
okay.
okay. You can unmute yourself.
Okay. Okay. I want to say something. Can you hear me?
Yes, we
Can
can.
anyone hear me? Yeah, okay. What about the slide for yesterday? Is the slide available?
Yes, it's available. I'm going to share it with Tolu so you can share it with everybody.
It's okay. Thank you.
Okay, I think Uzoma wants to say something. Right. Uzoma, you can.
Okay. Good evening, everyone. Can you hear me now?
Yes.
All right. So, I would like to first of all thank our facilitator, the park, for today's session. It was a job well done. Job well done on the CMP method. So our participants, as the messages have been going on the group chat and the Telegram group, and also the Google Classroom, and also via your mails. further information as regarding the upcoming sessions and the software to download, the links to the recordings will all be dropped on the Telegram group chat to be sent to you via mail also, and also the Google Classroom. So just do well to keep an eye on these three media so that you get briefed of all that is being done for the next coming section. And that being said, thank you all also for participating in today's session. It was very nice indeed seeing you all learn. I can see from the participants there are a lot of you that I know of, and it's encouraging to see that you have willing minds to learn.
I think Uzoma is having
The network
technical
is not
difficulties.
stable. Sorry, my dog also wants to learn geophysics. That's why it came.
All right, so I think I should close the meeting now.
Yeah. So it was nice
Thank
talking
you.
to you next week. And
All right,
please
see you next week.
Yes, and we'll start with the seismic data processing and modeling. Have a great day. Good night.
All right, you too.
All right. Bye, everyone.
Bye.